All right, fourth and final example. I'm going to take some shortcuts here just to save us a little bit of time, just for video purposes as well. So if we're going to factor this, we would find that we'd factor this down to 2x minus 1 and x minus 8 on top. The denominator would be x minus 4 and x minus 1. No, nothing cancels there, so what that tells me is that there's no holes, but we're going to have, in this case, two vertical asymptotes. I'm going to just give us final derivative here, just for time purposes. So when you take the derivative of this function, we end up with 7x squared minus 28 over the denominator squared, so that x squared minus 5x plus 4 squared. And the second derivative, p double prime, is equal to, we go through that process, we end up with negative 14, and in brackets we'll have x cubed minus 12x plus 10. That's all divided by x squared minus 5x plus 4. And that's to the exponent 3. All right, so as we go through then, I'm not going to go through the expansion simplification. If you want to take a look at what that looks like, or you can double check yourself, but my purpose here is to take this information and graph it. So, all right, so moving on, whatever you want to go after next is up to you. So we can go with max min, for example. The order doesn't matter in which you obtain the information. So your max min, this is where we let the first derivative, so let p prime of x equals 0. So that means that the first derivative, again, it's a rational function. So remember that when you have a rational function set equal to 0, you're simply just setting the numerator equal to 0, minus 28. Solving, 28 equals 7x squared, 4 equals x squared. So x is going to equal plus or minus 2. Plus or minus 2. So if we plug that back into the original function, we'll find out that we have a max min, and we don't know yet, max min at our two coordinates, negative 2. So you plug it back in, and what you find, you get, where's the function? Here it is. Okay, so if we put a positive 2 in, that would be a 5 times negative 6. In the bottom, we're going to have negative 2 and a 1. So we're going to end up with negative 30 divided by 2, so positive 15. And on the other one, so there are the 2 points, locations of the two max min. You don't have to listen to my muddling. Just easy to pause it, obviously. So there you go. So there's our max mins. So what do you want to do next? Doesn't matter. Let's do vertical asymptotes next. So with your vertical asymptotes, again, you're just setting denominator equal to 0. So that means that, therefore, we have vertical asymptotes at positive 4 and positive 1. So we have two vertical asymptotes. Horizontal asymptote, we analyze the function for the limit as x approaches infinity, p of x. So the limit as x approaches infinity, we're going to divide by x squared minus the 17x over x squared plus 8 over x squared all over x squared over x squared, 5x over x squared, 4 over x squared. That's just going to go to 2, 0, 0, 0, 0, and a 1. So that leaves us with 2. So horizontal asymptote at y equals 2. So the horizontal asymptotes are taken care of. Really should do end behavior since we do have vertical asymptotes. So that's the next task here, and I'll do it off to the side here. So end behavior. All right, so end behavior. As we start to look at the end behavior, so we need to do the limit as x approaches 4 from the negative side for 2x minus 1, x minus 8 over x minus 4, x minus 1. We want to do the limit as x approaches 4 from the positive side, same function as above. We also want to do the limit as x approaches 1 from the negative side. Again, the functions listed above. And the limit as x approaches 1 from the positive side for p of x. Still doing a little bit of thinking here. So if we have a number less than 4, so a little bit less than 4, just trying to think if I have to worry about. Okay. So if we go, let's go with 5, for example. So that's going to be a positive. That's going to be a negative. That's going to be a positive. That'll be a positive. So our end result then is negative infinity as we do the analysis as it approaches that particular value. I'm going to do that right. Let me think about that. So, one sec. If we do it from the negative side, oh, I should be putting in, yeah, negative. Oh, I should be putting a 3 in. I'm thinking of it as, sorry, I'm thinking of it as negative 5. That's not right. It's 3 that we'd be putting in. So that'd be positive. That's still going to be negative. 3, that'll be negative, and that'll be positive. So it should be positive infinity. All right, process is good. I just can't think straight. So now, looking at the limit as we approach 4 from the positive side, so we're putting in a number bigger than 4, so let's put a 5 in. So it'd be positive for the first bracket, negative for the second one, positive, and positive. So negative infinity. So approaching 1 from the negative side, so I'm going to put a 0 in. So that'd be a negative, 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 and a negative. So all the negatives cancel out. It would go to positive infinity. And the last one, so let's pick the number 2. Positive, negative, negative, positive. So it too would apparently go to positive infinity. Now my only concern is that there is x-intercept in there somewhere. So at the moment I'm going to leave it alone, but I put a 2 in, so I gotta note that I put a 2. I better check for x-intercepts because x-intercept is a critical value, so I can't pick that particular value if I can't pick that 2 in the analysis if it's in fact outside or past an x-intercept. So let y equals 0. So if we let that function equal 0, so the original function, do it in factored form, 2x minus 1 and x minus 8, x minus 4, and x minus 1. We're really just setting the numerator equal to 0, x minus 8. So therefore, x would be 1/2, and x would be 8. So when I did the analysis of 1 from the negative side, my problem is, I'm pointing this out, critical value of 1/2. When I did this one here, I used 0, so I can't use 0 because the 1/2 falls in between it. So I got to go back and redo that third analysis. And I can't use, so I got to use something a little bit closer to 1 because I can't go to past 1/2. So I'll just pick something smaller than 1. So let's go with 0.9, for example. So if I put 0.9 in there, that's still going to be, that'll be a positive for 0.9, and that'll be a positive for 0.9, and that'll be positive for 0.9, but that becomes a negative. So in the end, this is actually going to negative infinity. So the one I was worried about actually worked out just fine. All right, and then let's just grab a y-intercept just to finish this off. So my y-intercept, we let x equals 0. So the function p at 0 would equal, back to the original function, be 8 over 4, so it would give us a value of 2. So therefore it's 0, 2. So now we have a whole bunch of information that we can plug into the graph. So let's label all our information or bring it across. So I've got vertical asymptotes at 4 and 1. So let's start there. So I'm just going to pause it while I mark everything on for you. Okay, so just bringing you back to what I've got labeled. I have everything labeled except I'm just putting my max mins on. So 2 and 9. Just be careful when you're looking at my graph here, match up my scale. And 2 and 9 was the one max min, and -2, 25 over 9. So I know that 3 times 9 is 27, so it's pretty much 3. So -2 and 3, so it's in this area here somewhere. Okay, so this is the information I'm given. Let's put n behavior on. So my n behavior, I know that approaching 4 from the negative side, or from smaller than 4 goes to positive infinity. So that means it's going to exit here, up top. So draw it in a little bit bigger. It's exiting that way. I know that if I go to the other side, oh, so I did it on the wrong side. 4 on the positive side, which would be over here, exits with positive infinity. No, sorry. -4. 4 from the exit. I was right. And then it exits, sorry, down here. Having a little bit of trouble flipping back and forth here. So 1 from the smaller side is negative. So it's down here, but it exits up here based on our end behavior. So now you're looking at the graph, and the question is, from your experience last semester in the 4U course, can you finish the pieces? Well, I know this is a max min up here, put an M, so it does look like a min. This quadrant, the one on the right, there's an x-intercept, and I know that it fits like that because there's no max min. I know that this is a max or a min, so it's the highest point, it looks like. So it's going to go through the points and then follow our asymptote out. So you're doing it from experience from last semester, and that's what you're really going with when you do a lot of these. If you need more information, you can get inflection point. You could get concavity or use the concavity test. So it's really, I'm giving you a whole multitude of tools. You really are it's up to you as to what tools are required for you to come up with a relatively accurate sketch of that function. So that being said, I'm not going to go into the 5th example. Looking for the assigned homework. I think it should be on your printout, if I recall. We're looking at page 240, 1 to 12. So obviously, long lesson. Normally I would teach this. It would take a whole period to go through 4 examples. So that being said, it's probably going to take you a day or 2 to work your way through those 12 questions. So if you do have any questions with the graphing process, I'll be able to help and work your way through. Good luck.